Good afternoon. This is Mike Mazzarese with AST. Thank you for joining us. This is the fifth webinar in our spring series, and we'll be talking about the RDC process. The formal title, Leveraging the RDC Process to Develop Surgical Designs and Manage Expectations. I'll be giving the bulk of the presentation. Dwayne Guilfoyle, President of AST, is going to jump on about the last 1/3 for a case study. So as I mentioned, this is the fifth. We've got 3 more in the spring series in 2020. So starting next week and through the end of May, we'll be focusing more on the application side. And so next week we'll be covering slurry injections in overburden and challenging geologies. The following week, we're going to focus on fractured bedrock. And so we're going to, all the discussion today is really going to focus on overburden characterization. Fractured bedrock characterization is we're going to basically translate everything we talked to today into bedrock in that session. So if you're interested in bedrock characterization, please join us on May 19. And then the following week, we're going to wrap up with permeable reactive barrier design and installation. So the RPI group consists of 3 entities. Up at the top, we've got RPI. So shout out to them, to Bob and Scott, for hosting this today. They are the developer of the technologies that we covered in the previous webinars. If you're interested in any of those, please let me know. They're posted on the Trap and Treat website. And they also, specifically pertinent to this conversation today, they operate what we call a project support laboratory that we're going to reference quite a bit. AST, the company that I work for, we're the global distributor for the technologies. We're also tasked with project assessment and design, as well as field QA/QC. We launched a new website a few weeks ago, so please feel free to check us out there at astenv.com. And then lastly, the third leg of the stool is our authorized installers. And so today we're not focusing on injections, but our installation partners here in the States and around the world are familiar with these RDC techniques that we're going to talk about today, so we can implement them on sites pretty much around the world and get those samples back to the RPI lab that's based in Denver that we'll touch base on here shortly. All right, so here's our the bulk of the work we do is in the States, Canada, in Europe. Most of our sites are in Scandinavia, but you'll see the note down there at the bottom. We have worked in UK, France, Italy, and then there's a couple others there as well. Okay, so we wanted to break out we wanted to break out one of these webinar sessions on the RDC. And so, why do we put so much emphasis on that? If you've worked with us in the past, it's something that we try to employ on every site that we work on. So why is that? So, first off, I like to say everything works in a beaker, right? So all of these technologies are developed in the lab and they work, treatability tests generally work, as long as it's the right, the technology's appropriate. And why do things work in the lab but not necessarily in the field? And so it comes down to a couple things. So first is longevity, and that's a characteristic of the individual technology. So we're not going to cover on that today. That was kind of covered in the previous webinars. Next is going to be contact, and that's really the focus of the next 3 webinars is on distribution. Third one, in situ remediation is going to hinge on having the proper dosing. Okay, dosing is going to relate, obviously, it's going to tie into the characterization work, how much mass is present. Okay. And so that mass, now this presentation focuses primarily on source area characterization, the plume characterization. So how this translates to like distal plumes will come in more when we get to the PRB webinar at the end of May. So we're talking about saturated soil mass, and it's very complexly distributed almost always, right? Even if you have a sand site, as you have a siltier sand lens, mass is going to distribute differently, right? So what's good is to have, it's good to have good delineation vertically, okay? And we'll get into that here in the presentation as we go. And what's really important is to have, as that lithology changes, have soil samples that span those multiple or those varying geologies. A lot of times the mass contribution in the sorb phase is underestimated, and that's just because, again, it's a quantity issue, or maybe it's even, a lot of the data that we review, it's usually thin and old. Some samples that are 20 years old, we really can't use that for current remedial designs. Next, we see, high-res tools like the MIP and the UVOS have been around for a long time, and they're great tools. However, they don't help us because since they're not quantitative, the results are not quantitative. They don't help us from a design perspective. So you can't take a 10 to the 6th response on a PID that you'd see with a MIP and translate that to X milligrams per kilogram of soil, GRO. It doesn't work like that. So you've got to have, if you're using those tools, make sure you've got a robust sampling program on the back end. And then lastly, my client won't pay for additional characterization. And so if you've got that site that's been around for 20 years, and more often than not, what we have is 20 years of groundwater data. That might be like a 30-page PDF, and we've got a half a page or 1 page of soil data. And so from a design perspective, since the bulk of the mass, 50 to 90%, say, could be locked up in that sorb phase, I would almost prefer the inverse of that. Okay. And so what we'll talk about as we go through the presentation is how the RPI group and utilizing the project support laboratory can help with that, can help with this last bullet. Okay. So what is an RDC? It's a detailed understanding of vertical and horizontal distribution of speciated and total mass. And so since we primarily work with activated carbon-based technologies, having the speciated data is obviously crucial since we're running sorption isotherm calcs for the individual constituents. But we also, kind of analogous to when you're doing a chemical oxidation design where you're looking at total oxidant demand. Same thing here. We've got to account for all the mass that's in the system. So we need benzene, but we also need GRO, for example, and that's really important, knowing that not all states are going to require that analysis, but from a design perspective, it's something that we need. And so the RDC is a collaborative process that we work with our consultant partners to be able to just find the data gaps, fine tune the conceptual site model, and then work with them to develop a surgical remedial design. And so just from this isn't a hard and fast rule, but in general, we're grabbing soil samples from every, say, 1 to 2 feet vertically. If you have any distinct lithological changes, it's always nice to have data there. We always tell our clients to err on the side of grab as many samples as is necessary for us to really understand what's going on the site. So that requires samples every 6 inches through a specific zone. Please go ahead and do that. From a groundwater perspective, if we've got a 20-foot screen, we want to break that down into, let's say, you can use like a hydro punch tool, or you could set nested wells to get some vertical delineation with groundwater as well. And this process is recognized in the recent ITRC guidance document. If you need a link for that, please let me know. And so just a few figures on the right-hand side. This is a carbon tetrachloride site. It's a grain elevator site in the Pacific Northwest. Our partner company, BB&A, went out and advanced 10 soil borings, collected 91 soil samples in 1 day. He did mention it was one long day, but still 1 day. And they converted these into temp wells and grabbed groundwater samples as well. So that's a lot of intelligence to gather in just 1 day in the field. You can take that, and this is not that site, this is a different site, but you can model that. And how this is different from like an MIP 3D image is that this is actually quantitative. So that essentially becomes your roadmap for your injection or for your remediation efforts. And so we take that, we translate that into a site map, we break the site down into different injection areas, and each of these areas is broken down vertically as well. So this is what we mean when we refer to a surgical design. So here's an example of here's some data from a site that's here in Colorado. This is diesel. These are diesel values in milligrams per kilogram, and these were all analyzed at the RPI laboratory. This is not a cross section; it's just a compilation of some of the borings. And so you can see that for one thing, you've got percent level diesel in soil, and there is really no in situ technology that's going to be able to deal with that, be able to get that down to some low value. Now, if you know it's there, you can manage it by, let's say, injecting a technology around it to manage the flux out of this zone, which is what was done out of the site. But knowing that it's there really helps us manage expectations. What you also have is, you can also see that you have, in this one boring, multiple orders of magnitude swings within a relatively, 6-7 foot interval. You've got 3 order of magnitude swings between your soil concentrations. And so when we divide the site down vertically, this is what we do, because it's otherwise what you're doing is you're basing your loadings off of, say you advance a soil core, you collect one sample at your high PID. If that's your 3%, we're basing it off of that 3% value and not optimizing the product vertically. And so that optimization effort is almost always going to pay for itself. And we'll get to the economics here in a few minutes. Here's another site where this process was performed. This is a chlorinated site. These are PCE all the way down through vinyl chloride in soil in micrograms per kilogram added together. So this is total chlorinateds in soil in micrograms per kilogram. And so, a couple things that stick out here. On this site, we had a variable refusal depth, and so we're able to map that out. But you'll see that there's variability similar to the previous slide. And what also to note is that we've got some really shallow chlorinated mass. Well, you can't use injection technologies for that. So this is sort of where combined remedies come into play. And these two wells, TW13 and 14, interestingly have very similar groundwater concentrations. And you can see you've got some higher concentrations here. This is pretty homogeneous, but the groundwater concentrations were almost identical. So if you were designing off of groundwater, you would fail here because of these values, this value right here, this 7 ppm that's sitting at 6 to 7 feet BGS. All right, so spend a few minutes on economics. And so most of the time, and I'll show you a couple examples here in a minute, it's going to result in project time and cost savings. Not always, because it's what's going to happen, because in some sites, and especially on sites that tend to have less characterization data, you're gonna discover, you're gonna hit a landmine. You're gonna have some undiscovered mass that wasn't accounted for in the original design, and I'll show you an example of that here shortly. But it really helps us manage expectations, because now we know exactly how much mass is there, and we understand the technologies that we're employing and how long they're going to be active, how much mass they can handle. And so do we have to come back in a year and a half, 2 years to do an additional application? Does a combined remedy make sense? Does it make sense to come in and do some surgical digs, or to flush with a surfactant first? And so it really helps with decision making, and that's all kind of tied in with this image that you see on the right. And this comes out of that ITRC optimizing injection strategies and in situ remediation performance document that I referenced earlier. And so you can see when you get to the phase 1, phase 2 preliminary investigation phase, costs and the time are the same, but where they diverge is where you start the RDC process, where you're going to incur some additional cost on this during this phase, but it's going to ultimately shorten the project time frame and thereby also save some money long term. And that's tied to a couple of things, right? So it takes out some of that, takes out the iterative process of sampling and remediation. So instead of going through multiple technologies or having to go through multiple rounds of investigation, that's all done up front at once. So here's one example. This is a corner gas station. Preliminary design is up at the top row there. So 5,000 square feet, 4 to 20 foot thickness, 21,500 pounds of Boss 200, 11 field days, $153,000 was our budget. They went out and did an RDC, so under $6,000, which is going to be representative for most, say, small to medium size gas station sites. And then the optimized final design, even though it came in at a larger footprint, we were able to trim down the vertical thickness. We were able to optimize where the product went, and that ended up saving product as well as field time. And when you add up the final design, the RDC, we come in at a little over 121,000, so $31,000 in savings for this project. We'll contrast that with slightly different situations. This was an emergency response, very limited information on the front end. And so the preliminary design was for just under 9,000 square feet, 4 to 12 foot thickness, 35,000 pounds of Boss 200 and about a $330K budget. The final design, as you can see, more than doubled the treatment area. So we're talking about, half an acre. The treatment thickness was comparable, but you see the Boss 200 didn't scale with the treatment area increase. That's because we were able to optimize where the product went. Field days were higher, as you would expect, given that treatment area increase. So the actual cost was higher when you add the RDC. We came in $109,000 over budget, over the original preliminary design. However, this doing all of this initial characterization and this additional remediation work on the front end is going to shorten the overall lifetime of this project, because you would have had to have come out as they sunk wells, and that's kind of eliminated that iterative process all on the front end. That was all fueled by the RDC work that was done on the front end. Okay, so here's the lab capabilities of the RPI Project Support Lab. I think I mentioned that they're based in Golden, Colorado. That's where the lab is located. So now we'll get into a few project summaries. The one thing I don't have a slide on is, if you're interested in sending samples to the RPI lab, I would just say we could either handle that in the Q&A or reach out to either Dwayne or myself, and we can help guide you through that process. Okay, so this is a small gas station. We did 5 RDC soil borings. You can see that in May 2016, we collected 40 soil samples from 6 to 20 feet BGS, and then we came out a few months later to do the installation. So here's the log for PB1. You can see we've got this sandy silt on top of this highly decomposed granite, and so we had theorized that most of the mass is probably sitting at that this change in lithology. And this is the soil sample data with depth for that boring. And we collected soil samples at each of these depths, so 6 all the way down to 20 feet. We found mass at one interval. 14 feet was pretty heavily impacted, and so groundwater was at about 8 feet BGS, and so it's still best practice to inject some material up in the smear zone above this impacted zone. But we were able to bracket from 12 to 16 feet, which was pretty close to our refusal depth. We were able to bracket this area. We added a lot more material than we did up here. And obviously this is, since there was only 40 soil samples, 5 soil borings, this was all completed in one day. And we do have a project summary for this site if you're interested. It's got a lot more information than what I'm going to present today, but here's just your pre and post. This is baseline, and then 24 months after injection when they were able to close the site. See the you can see the benzene concentrations decrease 1 to 2 orders of magnitude. Okay, so we'll cover another site here. This one's a little bit larger. This is a pipeline rupture in southern Michigan. So the release occurred in 2000. You can see that we had about 1,700 barrels released. 1,400 barrels were recovered during the initial response. There was some excavation. There was also a groundwater extraction system installed. This was all done before we got involved with the project. So we'll focus on the RDC. So we had 34 soil borings were advanced down to bedrock, sampling every 2 feet. And those samples, were all sent to RPI and analyzed for speciated VOCs as well as total hydrocarbons. And then we also installed 34 nested well pairs in those boreholes, looking at shallow and deep groundwater down to bedrock. And those were analyzed for VOCs, TPH, as well as anions. And all those analyses, like all the projects that we're going to talk about today, they were all sent to the RPI Project Support Lab, and the analyses were performed pro bono. So this site, the one nice thing about I mentioned before about having all that RDC data is it helps set expectations. And so expectations were set that this was going to be a multiple. This was going to be, since it was an LNAPL site with some source material that we didn't have access to, we were going to be out there for a while and we were going to have multiple injections. So 1 year after the first injection, they came out and did a second RDC for really 2 reasons. One is to see how we did, check on performance, but then also to design the next phase of work out on the site. This was a little bit smaller. There were 12 soil borings advanced, but they were adjacent to original boreholes that were done in the first phase of work. And then we also looked at groundwater, and then lastly we looked at distribution in the soil cores. So here are the mass reductions in soil and groundwater for benzene and TVPH, which were in line with our expectations. And again, this information was used to design the 2016 second application out on the site. And this site also has a project summary drafted with it. If you're interested, we can get that to you. And this site actually had a third injection event in 2018. And the injections are getting smaller as we go, smaller in scale. You can see here's the benzene over time. Baseline, assuming at day 0, we're out at day 2000 now with 3 injections in place in this area of the site. And so you can see the benzene concentrations north of 4,500 parts per billion have decreased down now to low ppb levels. The orange is the sulfate. So that's something else that is we really haven't focused on yet, is the support that the RPI lab gives you on the back end of projects. So there are really kind of 3 phases that they get involved. One would be the RDC, which is the main focus for today. Quality control testing. So if we're out on a large site, we can send them samples kind of as we go. And then lastly, on the confirmation sampling side, there are a lot of really specific analyses that RPI runs that are tailored to the technology. So for example, on a BOSS 100 site, which is used for chlorinated solvents, they're looking at dissolved gases like acetylene and ethylene. So I'll switch it over now to Dwayne Guilfoyle, and he'll present this this last slide.
All right, sounds great, Mike. You're gonna give me control.
Yeah, so you should have.
Yeah, this is another project in Michigan, actually in Ann Arbor. It was a large brownfield redevelopment project. A little background on the site: had been developed since the early 1800s. There were a couple dry cleaners that were located on the property, a car wash, a junkyard, many other commercial and residential uses over the last couple decades. And so there were various environmental investigations that had been completed at the site before we got involved. which we began activities on the site in the spring of 2018. And those previous activities had identified significant chlorinated solvent impacts in the soil and groundwater, and there were some previous remedial efforts that had gone on at the site as a part of some future development activities, but they had failed, and it actually had stalled the development activities based on the environmental challenges. I also want to pay special thanks to Agnes Taylor and Mark Quimby of SME for partnering with us on this project. So moving forward, Mike, you may have to advance them.
Good. Try it now, Dwayne.
All right. Yeah, there we go. Just slow. I get it to move back. Sorry. A little challenged here. So talking a little bit about the project, there were significant data gaps when we got involved in the project. They were looking at installing a PRB along the property line as part of the redevelopment activities. A new owner had bought the property in 2017 timeframe. So when we got involved in the project, we started looking at a lot of the information that was provided. Very complex site. The very heterogeneity of the actual soils itself, sand, silts, clays, which also affected hydrogeology of the site, aquifer characteristics. I'll show you a little bit of that in a minute, that there were multiple hydraulic conductivities that had been obtained from different consultants throughout the project. There was also constraints associated with the overall development itself, that there was a short construction window in order for us to be able to get any environmental work completed. And there were buildings that were already in the process of being constructed. In on that figure, you can see on the right-hand side that there was a narrow area of 20 feet wide that we had access to be able to install a PRB to manage the mass that was leaving the site itself. So, small area, relatively small budget, and, with all the failed remediation attempts, it was a significant challenge. So when we looked at the project, we put together some preliminary estimates, and we used the hydraulic conductivities that had been obtained historically, and you can see that there was a low, medium, high, range of from 40 feet per day to 257 feet per day. So when we use that along with the gradient at the site to develop the mass flux, that no matter, even if we use the lower hydraulic conductivity, that we couldn't fit enough of the BOSS 100, which was selected as the remedy for the PRB, within that 20-foot wide footprint. So there was a certain amount of source treatment that was going to be necessary in order to be able to reduce the amount of mass that the PRB was going to see during the 30-year expected lifetime that was planned for. So there was really two options to move forward with the project, and SM&E was evaluating whether to just use the existing data that was there, try to apply some safety factors, and use contaminant mass flux to be able to develop the overall PRB itself. But there was a high uncertainty of what that PRB life would be and how the performance would play out over time. So option two was to perform remedial design characterization, which would develop a high confidence in the remedy selected and then the overall long-term performance. So the goal of that RDC, just like Mike has said, is that we're trying to obtain the distribution of the total mass within the formation, but also determine how much mass that the PRB would have to handle. So in other words, we're not relying on flux and estimates of hydraulic conductivity, and it's really truly understanding how much mass you have at the site so that you truly can put enough treatment in place in order to be able to handle that for the long haul, for the 30 years of time that the PRB must exist. So they moved forward with doing the remedial design characterization in order to develop some more confidence and certainty in the overall remedy. So the RDC involved the installation of 79 soil borings to 40 foot below ground surface, where the borings were logged continuously and then samples were collected every 2 vertical feet. As a part of that, we also installed 46 nested groundwater well clusters that had 3 to 4 discrete intervals at each location with a 5-foot screen with these, you can see down in the right-hand corner of what that cluster would look like. We gauged each of those and collected samples of groundwater. In addition, performed slug testing on some 2-inch wells that were installed within the PRB. So a total of 1,120 soil samples and 185 groundwater samples were analyzed for CVOCs, and then the groundwater was analyzed for dissolved gases and anions. All of those samples were performed by RPI in the support laboratory. In addition to that, we did some additional hydraulic calculations to develop the overall mass flux that was going to be seen at the property line. So this is just some figures here showing the soil boring array that was completed to map the plume. The spacing of the soil borings were on about a 30-foot grid pattern across the site. The groundwater well clusters were on approximately 40 to 50-foot spacing. So what did we find during the RDC? We determined the total mass in the formation. There was 4,125 pounds of PCE mass present within a 60-foot wide band, moving from the source area to the actual property, downgradient property line, which is where the PRB was planned to be installed We did find DNAPL concentrations in the source area as much as 4,640,000 microgram per kilogram in where the wet well was that sit right outside of the actual dry cleaner. And then the groundwater concentrations were all within the same magnitude that had previously been identified at the site, but were more pervasive. And then the PCE mass was 99. I'm sorry, the mass was 99% PCE. There was not any daughter generation there just because of the oxic and groundwater conditions. So with all that information, and now we know where the total mass is and how it's distributed at the site, the overall remedy that was developed involved the treatment of source and mid-plume contamination up in this area here in order to be able to reduce the total mass that would eventually hit the PRB down at the property line. In addition to that, there was a PRB that was installed in this location here in order to manage any mass flux that was coming out of the source in the mid-plume area while that treatment was occurring in the source and mid-plume. And then finally, a PRB was installed at the property line that really handled the mass that remained underneath of this building that was already in the process of being built. So it truly was just handling what we knew to be the overall mass. It didn't matter when it would get to the PRB. We just knew we had treatment enough in place to be able to handle that over time. So the actual implementation, the pilot test was completed. Sorry about that. Pilot test was completed in 2018 and then ran into February of 2019 for the actual monitoring. And the full-scale injection occurred in the spring and summer of 2019, where there's now been 2 rounds of groundwater samples collected from the site. PRB1, which was in the mid-plume area, has had a 99% reduction in PCE concentrations, and then the PRB2 at the property line has had an 80% reduction, meeting the overall goal, but it will continue to trend down as the mass is being managed in the overall source area. And then these are some pictures of the site with the building being built. On the left-hand side, the overall PRB1 set up in this area, and the source area was to the north of that. And then this is that little sliver of property that's 20 feet wide where we had the ability to be able to install the PRB. So very small footprint. That's actually one of the monitoring wells within the footprint of the PRB itself. So we're going to move on to questions. I want to say thank you for your time, and then we're going to have Derek Pizarro join us here and help us monitor the overall questions, and Mike and I'll try to address these as we move along. Mike, I've got some questions here while we're waiting on Derek to join us.
Sure.
I'm reading some here.
I'm here. Sorry, I was muted.
Yeah, go ahead, Derek.
So yeah, we got a couple questions here from the audience. Also, while we're answering some of these questions here, feel free to type them into the questions box in the GoToMeeting, and we'll try and address all of these. I do want to thank everyone for their time today. I know it's crazy time, so thank you for spending an afternoon with us. And if for some reason we don't get to all the questions today, or you think of something in subsequent hours or days, please feel free to reach out to any of us. Dwayne and Mike have their contact information up on your screens. First question, how do I send samples to RPI group? Are there any special shipping requirements or costs associated with it?
So the overall shipping is just like sending to a commercial lab. You're going to package up in a cooler. RPI provides a electronic chain of custody. I think it's probably easiest for you just to reach out to one of us at AST to help guide you through the process. There is some specific packaging requirements that are necessary because of the USDA, which is a permit that RPI has that they fall underneath of because they receive samples internationally. As part of that USDA permit, that any samples sent from a quarantine area, which most of the area in the eastern part of the U.S. involves a quarantine for fire ants or Japanese beetles, and so it just takes some additional packaging and then some placarding on the coolers, but we'll help you through that whole process. We have a PowerPoint presentation that's can walk you through how to get that done. It's not that difficult.
All right. I got a two-part question here from one of our audience members. How do we account for inherent heterogeneity of soil samples? Are we compositing? Are we mixing? And with all the borings you're taking out there in this RDC, how do you eliminate preferential pathways or daylightings when it comes time to inject?
Well, the samples should be discrete. We're talking about 2-ounce jars, and so you're, hopefully, we're not going to composite a, 1 foot section or say a 2 foot section out of a macro core. We're going to grab, an inch or two of soil from 15 feet, for example. And so, and because you are collecting such a dense quantity, if there are any outliers from, collecting, because then again, they're taking a small sample when they get to the laboratory. If there's an outlier, then we can throw that out because we've got enough samples to base that decision upon. And when it comes to actually completing those holes, what's really important actually is, abandon those holes properly so we don't have that preferential pathway. And what our SOP for that is to backfill with hydrated bentonite and use a solid tip, larger diameter than the macro core, to be able to compact that hydrated bentonite in several lifts. And that's actually what we do when we get to the injection phase as well. But that's really good to do. And also, if you're doing, say, anything like MIP work or anything else on the front end, otherwise, when you get to the injection phase, you're gonna, find all those borings.
Yeah, I'll just add something to Mike's comment related to the heterogeneity of these lithologies. I mean, that's the power of not being handcuffed with the amount of samples that you can collect. So if you're in a within a 2-foot zone of soil and you see a change in lithology and a high PID reading, even though we just give recommendations of samples every 1 to 2 vertical feet, you as the practitioner, you can collect as many as you want in order to be able to build that conceptual site model. I mean, you have the power in order to be able to do that because you're not handcuffed with the number of samples that you can collect. So the more the samples, the better.
All right. And staying with sampling here, another 2-part question. Do states accept RPI's data? And is the data like you provided in that diesel LNAPL table, is that how it's made available to the client?
Well, the second part, it's no, that's not. I mean, that's something that we work with, our, depending on the project, us at AST, we can help, manipulate the data that comes from the lab. That's not how it comes, obviously. So that's something that we work with. When we get to the design phase, we can distill that data down into the format that you saw. And in the first part of that question of whether states accept the data, really depends on the state, but I would say most states accept it, but it's flagged. And so if it's flagged as being from a non-certified lab in that state. So RPI doesn't carry any state certifications. This information is not for compliance. It's just for filling data gaps, helping answer questions. Excuse me. And so it's not for compliance. Even on the groundwater side, on the back end, there's a lot of states that allow you to report it. It's just flagged with an asterisk, for example.
All right. And this next question refers to additional tooling use. In your case study or possibly at another site, would you say that MIHPT or an HPT tool would have served you well per hydraulic conductivities, or at least as far as they are concerned? Would that have been useful?
Yeah, so I'll speak to that related to the Ann Arbor project. It was used out there. They did cross sections across the early on. We didn't use it, but they had attempted to use it. We like that tool. It's a powerful tool, especially when you're designing PRVs to try to help with identifying these zones of high Ks or whatever. But the lithology was so mixed up, and the heterogeneity was just it was just all over the place. And so when they ran that tool, the data you were getting back was so random that in this case it just didn't help us. And that's really what drove the site to really look at trying to determine what the true mass was in the formation versus trying to obtain good hydraulic conductivity data in order to be able to develop a model based on flux in order to be able to design the PRV. It just wouldn't work at this site.
All right, and then we received a follow-up on that question. With all this data that we're generating, do you typically promote 3D modeling or visualization to your client or stakeholder? And and what's the value within that?
I think for complex sites, it's on the design end, we use it probably not as much. It's probably more for stakeholder presentations, but it's something that the RPI group can provide. We can provide the 3D imaging. But I don't know, Dwayne, do you agree with that? When it comes to the actual design phase of the work, I don't know how much that is utilized.
We still break down the site surgically. I'm with Mike. I think it's a great tool to be able to share data with client versus trying to show them you know, a plan view in an Excel spreadsheet, it's just hard for some people to visualize, you know, where the contaminant mass is. And I think it's just a powerful tool to be able to just, you know, once you get the RDC data back, to be able to sit down with the client, you know, as the, you know, as far as the consultant, and a lot of consultants take our data and then develop their own models based upon that.
Yeah, the only comment I would add on to that is
All right.
that if that's something that you're interested in, let us know on the front end so we can get all the RDC points GPS located while we're out there.
Okay, point.
Derek, I see one final
Next
question.
question.
I see one final question, Derek, here
Yeah,
real
I got
quick,
you.
related to the Ann Arbor case study, and the question is why was CAT 100 versus BOSS 100 used in the different locations of the PRB, and or not the PRB for the site, but so in the source area in the mid plume, CAT 100 was used because the DNAPL mass that was identified in the old dry well next to the dry cleaner area, so the concentrations were just so high, and the demand on the iron was too high for just BOSS 100 alone. So CAT 100 was used in the source mid plume. CAT 100 was used in the PRB1 and the mid plume location also, but BOSS 100 was only used at the property line, and that was predominantly to be able to limit the amount of daughter generation that would be created on the down gradient side, because BOSS 100 has the ability to be able to manage that, plus also give you rapid groundwater treatment to achieve your overall goals quickly at the property line itself.
And I've got one last question here. Have you ever used an RDC for a site involving the Army Corps or a DoD site?
Yes. Several. Yes, several at this point. Mm-hmm.
Yeah, and that data that gets generated, yes, is accepted by the Army Corps and DoD as far as for remedial design purposes. Correct.
All right. Well, I think that that's all the questions that got asked. If you think of one in coming hours or days, please reach out to either AST or RPI. Contact information in front of you there. And one last note before I turn it back over to Mike. We do have next week on Tuesday and then 2 Tuesdays after that. So the remaining Tuesdays in May, we'll wrap up our spring RPI group webinar series. So please look for our contact on both email and LinkedIn, and we hope to see you again soon. Mike?
Thanks, Derek. Thanks, Dwayne. Thanks to RPI for hosting this today. And most importantly, thank you to all that attended. Know your time is precious. So please reach out if you have any questions. And thank you again. Have a great day.